So, welcome back now onto the 8th lecture. We have started to look into the sort of a detailed picture about the surface and interfacial tensions. So, we are essentially continuing our discussion on the components of surface tension and various aspects of interfacial energy. So, what we will do a quick recapitulation. So, we now understand what is a surface and what is the fundamental difference between a surface molecule and a bulk molecule. So, this is a surface molecule which has lower coordination number as compared to a bulk molecule, and then we were considering the interaction, pairwise interaction between two molecules, between two phases, and for while doing that we considered the interaction or the excess pairwise interaction, pairwise excess interaction energy while the molecules were at the surface versus at the bulk, and then we could correlate it to the surface tension considering the total number of molecules present at the surface. Eventually we considered the interaction between individual molecules, defined the different coordination numbers, and under certain assumptions we could eventually get an expression like this for gamma 1 2, and with further approximation by considering that one of the phases to be a condensed a non-condensed phase or a gas or a vacuum, we could get expressions for gamma 2 and similar expressions for, this is wrong in fact, similar expressions for gamma 1, and that now gives us this particular expression. Now we can also use this. So, what we have is this. We can look into, so we start our discussion which we already did up to this point, and let us start our discussion from this particular state. So, what we have is where V12 is the interaction between one molecule of 1 and that of 2, and as we have already argued that this V12 includes the van der Waals interaction of course, and might include other parameters like the polar interaction as well as maybe the steric interaction, which we now understand, but we will not consider this in greater detail. So, we will be happy to look into the van der Waals interaction initially and then the polar interactions. We just reframe this equation in a slightly different format to essentially what we get out of that is we can write this as which is fine, but now let us consider another picture. Suppose we have a surface 1, object 1, these can be semi infinite, stretch in this direction, but we consider an object of 1. So, this is a surface, let us assume the surface areas are same, and let us also consider that they are initially infinitely separated away and we bring them together in contact. So, this is the initial configuration and eventually this is the final configuration. So, now if we look into the change in the energy between the final state and initial state, what we get is this. So, we look into the free energy at the final and the initial. The internal energy of each of the objects remains same, these are non-reacting system, there is no change in size. So, all that changes is actually finally these two objects are in contact, and initially the total energy at the surface was this. Now, if we compare this and this equation, what we get is we straight away get an expression for delta G 1 2, which turns out to be minus n z v 1 2. So, this gives us or allows us to get an expression for the change in the free energy when two objects come in contact with each other, but initially it must be understood that the two objects come in contact either in air or vacuum. Now, let us consider or take a slightly detailed look and look into the different components or different forces that contribute into this V 1 2. So, let us first assume that, as we have already told, that van der Waals interaction is omnipresent. So, let us first assume or consider only van der Waals forces. So, let us assume that V 1 2 comprises only of the van der Waals interaction, and as a consequence the delta G 1 2 we get is actually delta G 1 2 due to the LW component of the van der Waals forces. Now, at this point I will invoke some sort of a mixing rule that is prevalent. It is quite prevalent that for van der Waals interaction it is conveniently assumed is an under root of V 1 1 LW into V 2 2 LW. So, it is sort of a geometric mean. So, that also you can see here. So, that is sort of a geometric mean, and once you incorporate this into the equation that we already have, or the expression of this particular expression for delta G 1 2. So, I will just write down once more. What we have is delta G 1 2 is minus n z V 1 2, and since we are only considering the van der Waals interaction, therefore, we can further write it as minus delta G 1 2 LW is minus n z V 1 2 LW, and then once you incorporate this expression into this particular term n z V 1 2 LW, you can nicely write it as which you can further modify as it is just a bit of algebraic manipulation that we are doing. Just multiply the numerator and denominator by 2. This 2 now, if you take inside the under root, it becomes 1/4. So, it is half into half. This n z you also take inside the under root. So, it becomes n z square. So, you use one of the n z's here, one of the n z's here, anyway you have these two, and what do you get? You certainly see that you are getting an expression. These expressions are already known to you. This corresponds to gamma 2, but it is the LW component of gamma 2, and this is the LW component of gamma 1. Therefore, what you get is finally is this. Now, this is something very, very important and interesting. It is a pretty simple derivation, but it is quite interesting in the sense that now if we reconsider the expression of delta G which is delta Gf minus Gi, and we are considering only the van der Waals interaction, then what we get is delta G1 to Lw equal to Gf Lw, and which turns out to be gamma 1 2 Lw minus gamma 1 plus gamma 2 Lw. So, by rearranging, what we can get, we also plug in, let us say, from here the expression that we have already got about this gamma 1 Lw is, we combine this with the expression of G1 to Lw, which we already have, we get I will just write it again for all your understanding. So, all we do, we substitute the expression of G1 to Lw, which we have already got here, and once you do that, if you do a transposition, what you get now, gamma 1 to Lw is gamma, this particular expression, and this turns out to be which is a neat expression nonetheless, but there is some additional consequence of that. What is this consequence? Gamma 1 and gamma 2 both are positive real numbers. So, therefore, whatever is the difference, whatever is the numerical magnitude, their square is always positive. So, what it means is gamma 1 2, or we can generalize it as gamma ij, is always positive, or in other words, the van der Waals component of interfacial tension is always positive. What is the consequence of that? Consequence of that is, if you recall again, we got in the previous slide is, or one can also straight away say that the expression of delta G1 to Lw is this, and this is always a negative number. So, what does it mean? Two surfaces, two apolar surfaces in air or vacuum. Why I said apolar? Because there is no polarity, therefore, the entire interactions is due to van der Waals interaction. Air or vacuum will always adhere to each other. Why? Because delta G12 is negative, and we had already argued that any system which leads to minimization of energy is favored, right. The situation, however, changes slightly if the objects are coming in contact, let us say, through a liquid medium. So, we consider this, the same two objects 1 and 2. However, instead of air, now they are initially dispersed in a liquid medium 3. So, what is the GI? GI instead of gamma 1 plus gamma 2 is actually gamma 1 3 plus gamma 2 3, because this is a condensed phase as well. And these two now come into contact. So, the GF is gamma 1 2, and one can write the delta G. This is, please note carefully that these expressions or this particular expression is generic, it does not consider van der Waals interaction only, right, is this. Now, let us consider a very special case. Let us assume that these two blocks are of the same material, and which is a very practical situation, because you might have a colloidal dispersion. So, where all the particles are of the same material. So, the question now changes, instead of two different objects coming in contact through a liquid medium, two surfaces of the same material are trying to come in contact in a liquid medium. So, what is going to be the expression of delta G? Delta G is going to be gamma 1 1, so that is what you get here, minus this is gamma 1 3, this is gamma 1 3, this is 2 gamma 1 3. Important to note, gamma 1 1 is essentially an interface between two blocks of 1 and which is 0. So, this is 0. So, what you get is delta G is minus 2 gamma 1 3. Now, if you consider only van der Waals interaction, or in other words delta G is entirely constitutes of delta G LW, then what we get is gamma 1 3 LW. What have we already learnt? We have learnt that gamma 1 3 LW is always positive, because its expression is going to be gamma 1 LW minus gamma 3 LW whole square. So, what does it mean? That this entity, since this is always positive, this is going to be always negative. This one can physically explain in two ways. We have considered only van der Waals interaction. So, one can argue apolar colloids in an apolar liquid medium will never be stable. Why? Because their adhesion of the colloids with each other is going to be favored, and what eventually will happen. So, if you make an initial dispersion, the particles, because of the thermodynamics of the system, will join up. So, they will agglomerate and eventually it will settle out. So, from a practical standpoint, colloids of apolar material in an apolar liquid or a solvent are never going to be stable. This also implies that even in order to explain a very common phenomena like a stable colloidal dispersion, one in fact needs to consider the polar interactions, or in other words, you must have, as we will see in the subsequent discussion, that in order to have colloidal stability, it is mandatory to have some bit of polar interaction. And therefore, we now need to consider, in addition to van der Waals interaction, we have to now consider the polar interactions. So, let us see what are the components of these polar interactions we have. So, polar interaction, or they are commonly known as the acid base interaction. Interactions, and it is obvious that polar interactions are possible only when neighboring molecules have opposite polarity, and therefore, it is not as generic as, let us say, van der Waals interaction. So, you have to have when there are neighboring molecules of opposite polarity. So, you must have polarity within your molecules, and only then polar interactions are emphasized or are possible. Typically, to mathematically handle, there are two empirical parameters that are used to quantify AB type interaction, which are gamma plus and gamma minus. This gamma minus essentially corresponds to the electron donor or proton acceptor parameter, which are if you can recall your high school knowledge about acids. So, this is in fact, this represents a Lewis acid or a Bronsted base. Similarly, gamma plus is the conjugate parameter, or it is exactly the opposite parameter. It is the electron acceptor proton donor. So, it is going to be the Bronsted acid and Lewis base. And for any species I, gamma I AB, the polar component of surface tension is this. I repeat, please do not confuse this with the mixing rule that has been used for van der Waals interaction. I will show it to you side by side, so that you do not confuse. What we learned there is, or used there is, this particular relation, that is the interfacial, that is the interaction or the interaction between two dissimilar molecules due to the van der Waals interaction. We used a mixing rule which looks very similar, but please do not confuse. This is what we have used for van der Waals interaction. This is in fact the interfacial interaction, and that was a geometric mean of the individual van der Waals interactions. In contrast, in while we are considering the polar components, in order to describe the polar component of the surface tension of a particular material, we sort of use a very similar mixing rule, similar looking mixing rule, I would say, comprising the gamma plus and gamma minus component, that is the electron donor and electron acceptor, or the two conjugate parameters of polar interactions, right. What it also tells, that if this relation also tells either of gamma plus or gamma minus is absent, then gamma I is 0. This is very interesting, and in the subsequent discussion we will see how this manifests in different settings. Maybe before I stop this particular lecture, one more expression that is useful for polar interaction, and this is sort of assumed, is delta G A B is minus 2 gamma 1 plus gamma 2 minus plus gamma 1 minus gamma 2 plus. So, these are the two important relations that you need to consider for the polar interactions, and based on these two concepts we will now discuss in the next lecture about the colloidal stability and other issues of how two surfaces which are coming in contact behave in case there are polarity either in the liquid medium or within the surface. Thank you.